right. Thank you, Marcy, and welcome again, everyone, to our webinar today. Hopefully you've had a chance by now to download the WFCM workbook, which is shown here on the left, and downloaded the view-only version of the wood frame construction manual, 2012 edition, which is shown here on the right. If you haven't been able to do that, go ahead and do so now while we're doing some of this introductory material. So the workbook is printable, and so even if you don't have it printed now, if you want to print a copy out after the program, you should be able to do that. The wood frame construction manual, if you don't already own a hard copy or a printable electronic copy, you should be using the view-only version that's available on our website. Before we jump too far into that, I'm going to ask Marcy, if she will, to take care of our first poll for us, which will give us an idea of who's in the audience with us today.
Absolutely. So the question is, what is your profession? Go ahead and vote. Are you an architect, engineer, code official, professor, or other? And we're just going to have a brief little time to vote here. Once we reach 80, I'm going to close the poll. 80%. Alrighty, 80%. And we'll share how many we have. 77% engineers, 10% code officials, 7% architects, 2% professors, and 4% other. All right, welcome everybody.
Okay, well that's great, and that's really helpful for me. Knowing that there are some engineers in the audience may try and help you all with a little more information about some of the background behind the prescriptive requirements. But first, let me jump here to our website quickly, just to give you a quick tour of how to get to some of these resources that are available, and some that we won't be able to cover today. But if you get to our website and you go to Codes and Standards, you're going to see a couple of links there for our main standards. The one today that we're looking at is the Wood Frame Construction Manual. And once you get here, then you'll see the various editions. We're in the 2012 edition today. Note there is a 2015 version out on the street. I mentioned that this is a free view only copy, and so notice that that's where you can go to download. If you haven't already checked on the link, the workbook is down here. And then I want to also point out these high wind guides over here on the right hand side of the page. In response to some builders and others who were looking for some specific, wind speed specific guides, you notice that we have guides from 115 mile per hour exposure B and exposure C all the way up to 160 mile per hour exposure C. And so just note that if you're in one of those high wind jurisdictions and you want something that is even more simplified than the Wood Frame Construction Manual, that those resources exist. These are all free downloads as well, and so here's a good resource for you if you need it. Also, I think we mentioned at the beginning that you will have taken a look at the Changes webinar, and so there's a link here to get to our online e-courses page. And so if you haven't had a chance to do that, you can go here, look for various programs. This one in particular that went through the changes is STD 315. You click on that PDF, and that's going to open up a set of slides for you, or actually it'll get you to a location where you can take a self-study course, and part of that self-study course is these slides. And I'm just going to go through a couple of those. That's why you didn't receive them today, because I just want to give you a brief overview of the code acceptance of the Wood Frame Construction Manual. This 2012 version is in the 2012 IRC and IBC approved by reference. And so within the IRC, the 2012 IRC, our 301.1.1 alternative provisions shows the Wood Frame Construction Manual as a document that's permitted to be used. and then R301.2.1.1 shows where you can use different various criteria once you get above that 110 mile per hour trigger that's in the codes. And so that's one of those as well that you can use in the wood frame construction manual. Now the thing you got to recall here, and I'll show you this in a second, is in the IRC, these wind speeds are still based on ASCE 705. So there's actually a conversion table to get you to the ASCE 710 wind speeds and wind speed maps that we'll be talking about today that are in the wood frame construction manual. So I'll show you that in a second, but just know that this trigger is based on ASCE 705, and we're using different wind speeds, higher wind speeds in the newer ASCE 710 version. Then in the IBC, which also references the wood frame construction manual, that's done in Chapter 16 in the loads section, and that's where it provides an exception to use the WFCM to calculate your wind loads per ASCE 7. And then in Chapter 23 on wood, when you get to 2308 on conventional construction provisions, which apply beyond residential construction, there are also allowances to use the wood frame construction manual. So just be aware that this is permitted for both residential and within certain limits that I'll touch on in a little bit, can be used for non-residential applications as well, as long as you're within the scope, meaning the wind speeds and number of stories and those types of things. So that's something to be aware of as well. So I'm going to come back here to the workbook, and I believe Marcy has another poll for us. So I'm going to ask her to come back and just kick us off with another poll.
I do indeed. The 2012 WFCM can be used to design A, single-family homes, B, light commercial structures, C, decks and other ancillary structures, or D, A and B only. Just a couple more seconds to vote. It is pretty evenly, well, not quite evenly split, but there are two answers that no one is picking. All right, I'm going to go ahead and close and share. All right, so 26% say single-family homes, and 72% say A and B only. So light commercial structures and single-family homes. All right, so Buddy, what is the real answer?
Okay, so those of you who picked up on that nuance with the IBC chose the correct answer, which is D, A and B, which is obvious from the title, single-family homes per the IRC, but within the requirements or the boundary conditions set up in the IBC and in the scope of the wood frame construction manual can be used for some light commercial conventional construction structures as well. And so, for example, if you had a single story structure that was slab on grade and was within the limits that we're going to outline in a few minutes for using the wood frame construction manual, you'd be able to use that for some light commercial applications as well. So correct answer is D, and that's one of the reasons we do this type of a poll, is to really point out that this document does go beyond its title to apply to some non-residential structures as well. So let's jump into the workbook. If you have that up on your screen or in front of you, we're gonna scroll down through there and take a look first at the forward and just highlight a couple of things with this example problem. This document, this example problem, is just a tool that we've developed to sort of help you work through the wood frame construction manual, which is a pretty handy design tool. It doesn't certainly replace engineering judgment. So there are both engineering and prescriptive requirements in the wood frame construction manual. This example primarily focuses on the prescriptive, but again, we'll talk about the background information that is in the wood frame construction manual and the engineering provisions that back up the prescriptive provisions. So for this example problem, it is a two-story residence designed to resist high wind, high seismic, and high snow loads. And we realize those aren't going to necessarily be a part of every design that you undergo. Depending on what part of the country you're in, you may have one or two of these loading conditions. If you're in the Aleutian Islands up in Alaska, you'll get all three, and we actually found a place that potentially has all three of those loading conditions. But we know that for the majority of you, you're only going to have to look at one or two of these loading conditions. But this allows you to take really see the scope of the wood frame construction manual to show the broader range of applicability there. So that's why there are all three load conditions. The other thing I want to point out is the design sequence. And so while the design sequence is typically roof to foundation, the way the codes are set up are based on the construction sequence, which is foundation to roof. And so when we get into the design process, just like we do in the code, we're going to start at the roof, and that means we're going to be starting at the back of the book. And so we'll be looking up some tables for rafter design that are near the end of the wood frame construction manual, but that's just sort of the nature of the beast that hopefully you are all familiar with. This is based loosely on an actual home down in Williamsburg, Virginia. We've made some modifications to it to sort of suit our needs for this example problem, but that's a snapshot of the home that was built in Williamsburg. A couple other things that should be helpful for you. There's some color codes that are used throughout the workbook. If it's a yellow color code, it indicates that it works, that this value could be used for design, but there might be multiple options that will be available to you, and so I think you'll see that as we go through. If it's a bolded value, that indicates that that's the value that controls in the design process. Green is good, that means it's okay, it meets the design criteria, and NG in red means it's no good, it does not meet the design criteria. Here are some of the abbreviations that you'll see throughout the document, so there's a key there for that. I'll point out that L's for the lateral load provisions. It also could be for a header span or some sort of span condition. S is going to be for shear loads, and U for uplift loads. And so when we get into connection design and start talking about lateral, uplift, and shear, that'll be pretty handy for you. So those are the ones I'm going to look at here first today as we jump in. Today we're going to look at this upfront general information and then cover roof story design, and then a month from now we're going to look at second story and first story design for the structure. So for the general information, we'll get a look at the building description, the loads on the building, applicability limits, the prescriptive design limitations, talk about load paths, and show you the checklist. So that's kind of the first half of our presentation today. Here's a building description. Again, pretty straightforward. We know that all houses don't look like this, but from a standpoint of some of the assumptions we're making in the wood frame construction manual, this is generally what you're looking at. I will point out that north is this direction here based on the key, so east and west are going to be important when we're talking about some of the walls, and there's an attic space here on the eastern side of the building, a vaulted ceiling over here on the west side of the building. I'm going to jump then to the building description here on page 3 in your workbook. If you want to go there with me, and you see the dimensions of this structure. It's a 40-foot by 32-foot box, and so that's the first floor plan. Notice the walls are labeled 1A in the north south direction, 1A and 1B. Then in the east-west direction, 1-1 and 1-2. So it's letters north and south, numbers east and west. The first number indicates the floor. So then down here we see the second floor layout, and so we've got 2-2 and 2-1 for the walls east-west, 2A and 2B north-south, and then our attic space and the roof system. What we'll be looking at today is the third level, and so we've got wall 3A over here. If you take a look at this little note down here next to 2A, 3A is actually the little triangular gable end above 2A, which is the wall in the second story there. So that kind of gives you an overview of some of the terminology. We'll see wall heights in this structure are 9 feet, so that's going to be important as we look at some of the footnotes. We've got a 7 and 12 roof pitch. We've got just about a 25-foot mean roof height. We've got 2-foot overhangs, and then we mentioned the 40-foot building length, the 32-foot building width, and then this dimension here, top plate to ridge height. Just tuck that away in the back of your mind. That's 9'3". That comes into play with some of the roof loads for both wind and seismic that we'll be looking at. Then we've got your window and door sizes here. That won't come into play until next month when we're looking at the shear wall design. But that kind of gives you an overview of the structure. We've got a stairway penetrating all levels, and so that goes all the way up into the attic space. We've got this bedroom here on the left, as I mentioned, that's got a vaulted ceiling, and then we've got this finished attic above the right-hand side of the upstairs here. So that gives you a sense of how it's laid out, and we'll be working through that part of the example as we go. But then let's jump into the loads and see what we've got here for loading condition for our particular example. And so again, as I mentioned, we're based on, in this wood frame, this version of the wood frame construction manual, ASCE 7-10, minimum design loads for buildings and other structures. And for this example, we've got a pretty high wind speed, 160 mile per hour exposure B. And in retrospect, I wish we had chosen 150 exposure B, but I think I mentioned earlier there's at least one place up in the Aleutians in Alaska that has a couple of these load combinations. I think down in Charleston, South Carolina, they've actually gone with 150 mile per hour exposure B. So I guess the bottom line is if we can make it work for 160, we know it's going to work for other wind loads around the country. So then for seismic, we're using the ASCE 710 simplified procedure, and so we're using seismic design category D1, and that's an IRC subcategory. So just make a note of that if you're not familiar with D1, D2. Those are IRC subcategories, and the vertical force distribution factor is 1.2. Let's see, the gravity loads are going to be pretty typical for our roof system we'll look at today. We've got a 30 pound per square foot ground snow load, a 10 pound per square foot dead load. Note here about the dead loads is that those assumptions are going to vary for some of the wind and seismic loads. So we are assuming 10 is sort of a baseline, but you'll see in the footnotes that we show a little bit later on that those can vary for the roof and ceiling assemblies in the footnotes, and so that's where the footnotes come in handy to allow you to do some different things. The floor live load for the first floor is 40 pounds per square foot. Second floor is 30 pounds per square foot, which is pretty typical. Attic is going to be 30 pounds per square foot for that floor system. And then our walls are 11 pounds per square foot So make a note down here for our deflection limits. This will come into play later for our as we look at deflection limits, but for our rafters with the ceiling attached, it's L over 240. Rafters with no ceiling attached is going to be L over 180. Our floor joists are L over 360. And then when we get to our stud designs, for this particular document, I think we've got a couple of different options, but L over 180 is what we're assuming for this particular example. So what I'm going to do now is I'm going to jump into the wood frame construction manual. And so if you've got a hard copy, I'm going to be using the bookmarks here to sort of navigate around. And so one of the first questions that we'll need to answer is, can I even use the wood frame construction manual for this particular example problem? So I'm going to direct you right away to Table 1, which is on page 2 of the wood frame construction manual, and see what the scope is. So for the wood frame construction manual to even be used, here are the scoping provisions that say whether your building fits within those limitations. So you see that we've got a maximum 33-foot mean roof height, 3 stories, and 80-foot length and width of the building. For our loading assumptions, you can see those here for partition dead loads, wall assembly loads, floor and roof dead loads. Our floor live loads, this is where we make the distinction between our residential and non-residential or light commercial structures. So for this document, we've got floor live loads of 30 to 40 pounds per square foot. And we know once you get into the commercial applications, those are going to go up to 60 or even 100 pounds per square foot. And so that's where you need to really pay attention and make the distinction if you're going to use this for commercial applications. That's why I mentioned a one-story building, slab on grade. Obviously, those floor loads wouldn't come into place. If you're on a top floor of a multi-level structure, then that might be something that where this could be used as well for some of the prescriptive solutions. But those are some of the limitations that you need to be aware of. We talked about the ground snow loads. Those go up to 70 pounds per square feet ground snow load. The wind loads actually go all the way up to 195 miles per hour. Again, these are the ASCE 710 loads, and we'll look at that table here in a second, that conversion table, to make sure you're aware of that. And then our seismic design categories are SDC A through D2. And so the other thing that I want to mention here before we jump away from loads, and I'm back in the workbook, has to do with, we get questions about tornado loads. And so some of you are maybe joining us from the Midwest, and maybe you're in Tornado Alley, and folks say, well, can this be used for tornado loads? And so I want to direct you to a document that FEMA put out, FEMA P361, that deals specifically with safe rooms. And here's a look at the cover of that document if you haven't already seen it. But if you want to take a look at this on your own, it does provide some pretty good commentary about hurricane loads versus tornado loads and whether or not you can map those out. So I can't take the time here today to go through that. It's probably a webinar of its own, but just know that there is some good commentary in this document that might help you in that regard. So let's get back to the workbook and move on into some of the applicability limits. And one more thing that I'll mention here, you see that we've filled in the blanks for some of these loading conditions. In the back of the workbook, I'm going to jump there to the appendix. There's a supplemental section that has some of these checklists and worksheets. So here you can see that there's a blank worksheet that has, similar to what we've laid out here, just some worksheets that you can use, print out if this is helpful to you, in your design process. So I'm going to jump back into the loads and where we were, and then move on into some of the applicability limitations. So we've covered the loads. We've talked about some of the supplemental worksheets, and so talked about whether we can actually use the wood frame construction manual. We see kind of at a glance that, yeah, we're within the loading conditions that would allow us to use the wood frame construction manual. So now what we want to do is we want to look at whether or not we can actually use the prescriptive provisions. And so what I'm going to do next is kind of walk through our design case here, and if you're taking notes, if you have a hard copy, notice there's a typo here. This design case that we have is actually 24.7, just a little shy of 25 feet, so you can make that adjustment if you want to your copy. But we're within that mean roof height, number of stories. There is a note in the WFCM that says that we can design this building as a 3-story structure for determining gravity and seismic loads, since it does contain a habitable attic. And so we'll be talking about some of those assumptions a little bit later on, but we are within the limitations here for that 3-story structure. And our maximum length of the building is 40 feet, which is within the 80-foot limit that you see here in this table. There is a similar table back in Chapter 3, and I'm going to jump there now. And so if you're in the wood frame construction manual, jump to Chapter 3, and there's a prescriptive design limit table here. It repeats some of those limitations. And the reason for this is, since we have 2 different sections of the wood frame construction manual, we've got a prescriptive section, and then Chapter 2 is an engineered section. There are some cases where we have some prescriptive limitations that would kick you into the engineered section of the workbook. Again, I can't take a lot of time to go through all of that, but just know that with the beginning of each section of the wood frame construction manual, you'll need to check to make sure you're within those limitations. So back in the workbook, I'm going to jump to the next page, and this again is telling us whether we are within the prescriptive design limitations. And the comparable table there in the wood frame construction manual is Table 3, and so you see here that we're mapping to that table in the wood frame construction manual with this workbook. Our joist spans are less than 26 feet. We're at 16 feet, so we're okay there. Our joist spacing max is 24 inches on center, and so we're at 16 inches on center. And that's a common question. Can I use this document beyond, with rafters or joists spaced beyond 24 inches on center? The answer is no. That would require engineering analysis. We don't, for our particular joists, have any cantilevers, so we don't have to worry about that. Let me jump down here to the floor diaphragm aspect ratios. So one of the things that's kind of covered behind the scenes that may be a little bit difficult to determine is these floor diaphragm limits. So here you see that we have a table referenced, which is 316B and 316C. So I'm going to jump there in the wood frame construction manual to Chapter 3, and again, if you're following along, you see that the index or the bookmarks here are a real good way to help you navigate through the documents. So I'll be using those and then expanding back out so you can see the tables a little more clearly on your screen. But one of the first things we'll need to do is make sure that our diaphragm, we have a sufficient roof and floor diaphragm to even work and determine what our minimum and maximum roof and floor diaphragms are. So in Table 316, A1, this is for our all slope roofs, so there's a reason it's asking me to go to B. Let me jump there real quick. And this is our floor diaphragm limits for wind. So we're in table 316B, exposure B, so make sure you're keeping an eye on which exposure category you're in. And we're in 160 miles per hour wind loads. And remember, our wall height was 9 feet, so we're going to have to interpolate between 8 and 10 feet here. So our floor diaphragm width that we have in the structure is actually 30 feet. And so we're actually end up having to do some double interpolation here, which is kind of a pain, but some of these tables we will not have to interpolate. So notice here that the floor diaphragm width of 32 feet, we work our way across to 160, and the minimum is 11. Minimum here for 28 feet is 10, so that's interpolated at 10.5 feet. Then for our 28, for a 10-foot height, we've got 12 and 14, so that interpolates to 13. And so we see that here, when we interpolate that minimum floor diaphragm, it's 12.5 feet. And then our max is going to be 80 feet, again, based on those same tables and that same interpolation here in the document. So we're well within those diaphragm limits. So I mentioned the commentary earlier, and you think, well, what's behind these tables here? Because you're talking about diaphragm limits, and I don't even know what my diaphragm is made of yet. So I'm going to jump quickly into the commentary so that you can see for yourself. And if you downloaded the free view-only version of the document, that does not come with a commentary, so I have to let you know that up front. That comes only with the purchase of a document. So you won't be able to turn to this unless you've actually purchased the document. But with the commentary, what you're going to see is that there are background calculations for each of these tables. And so I'm going to show you just once because I don't have time to jump to the commentary every time. But what's behind this table here in the wood frame construction manual for the floor diaphragm limits are the calculations here for the floor diaphragms that we assume, sort of a minimum floor diaphragm that we assume, and then we're going to give you an example problem here in this one for 150 mile per hour exposure B. It's a little bit different than the one we have in our example, and the minimum per code is going to be a 3-to-1 ratio, and the maximum is also 3-to-1, or 1-to-3 and 3-to-1. So those are some of the limits on the diaphragm. But then to calculate those, we're going to actually have to calculate based on a floor diaphragm load. So that's the load on the structure, and per the load table in the wood frame construction manual 2.5b, the load on that diaphragm for that 150 mile per hour exposure B wind load is 170 PLF. So we can actually calculate that, and then assuming a certain diaphragm from the wind and seismic standard, that's also one of our standards, we can calculate a certain diaphragm capacity, which in this particular case, with the assumptions that we're using, is 232 pounds per linear foot. So based on that, then we can determine what our minimum and maximums are for that building. So this particular table, this particular value is 14-foot minimum, and then we go over here to the maximum to calculate the maximum diaphragm length. And again, using those assumptions from the table, 250 pound per linear foot load, and in this particular case, 308 PLF diaphragm, we can calculate a maximum diaphragm length based on the length to width ratios. or sorry, that maximum limit of 80 feet that we put on the document. And then based on our aspect ratio limits, we got 3 different checks that we do. And so for this particular case, the 80 foot actually controls for min and max. So that's the commentary. That's a useful document that gets you into the background for all of these tables. So this little check here that we do comes from this table in the wood frame construction manual, but there's a lot of calculations from ASCE 7 that, as an engineer in the audience, I hope you realize if you've had to plow through ASCE 7 that we've done a lot of the work in calculating all of those wind loads and seismic loads and tabulating that information for you in Chapter 2. And then that carries over here into Chapter 3 to develop the limitations that we have for things like roof and floor diaphragms. So again, I'm not going to take time as we go through the rest to tackle all that background information, but that is what sits behind a lot of these assumptions. So for our floor system, our wall system, our roof system, which we're going to be looking at today back here in the wood frame construction manual, table W1.2, and I forgot to mention that earlier as well, but when we number these tables in the workbook, we're going to put a W in front of those. So when you hear me refer to W1.2, we're distinguishing that from anything in the wood frame construction manual, which might be just a table number 316B here. So we have that W to make sure you're clear we're in the workbook for some of these table designations. So this checklist here we've gone through already for our example and verified that we're within the limits, the prescriptive limits. Going to jump to the next page here now and just talk a little bit now about load path, because that's a pretty important thing too as we look at designing for wind and seismic loads. The wood frame construction manual makes it pretty clear that we want to maintain a continuous load path. So that's sort of an overarching statement in this document, and then we just define that continuous load path to cover both lateral and vertical forces down to the foundation. Here's an example just from one of the figures in the WFCM of how we look at the different shear connections. So within the wood frame construction manual, you'll see we're going to talk a lot about loads in 3 different directions for wind loads: lateral, shear, and uplift loads. And so this gives you a sense of how we're looking at those loads and how we're going to be designing for those as we work through the example. So another checklist that will probably be pretty helpful to you is this one, and now I'm on page 8 of the workbook. If you're following along, again, these blank checklists are all covered in the back of the workbook. And so the way the workbook is, or the wood frame construction manual actually is laid out, really lends itself to checking the load path. And so we start with the connections at the very beginning of the chapter in Chapter 3 of the WFCM, and work through the lateral and shear connections for roof assemblies, roof to wall, wall assemblies, then wall to floor, floor, then floor to sill plate, or foundation assemblies. And then we're going to look at our uplift connections and overturning resistance. And let me just touch briefly on the distinction that we make too for you, some of you West Coast designers who maybe don't do a lot of wind load design. When we mention the word uplift, we're talking about wind uplift on the roof structure. When we talk about overturning uplift, which maybe is a common term that you're using out there, we're going to talk about overturning resistance, and we're going to talk about hold downs. So just know when we say uplift in this wood frame construction manual and in this workbook, we're not talking about the uplift on the hold downs. Okay, so just that note and distinction as well. Then we're going to look at sheathing and cladding attachments, special connections, and then for today, we're going to skip past the floor joists. So we're going to skip past the wall assemblies, and we're going to go looking at the wood roof system. So we're going to be looking at two different sections, but as I mentioned, a lot of times we're going to jump to the back of the book because we're starting with the roof. All the connections are kind of handled up front, so we'll be kind of jumping around in the WFCM, but I hope you understand sort of how the layout works now in the wood frame construction manual, and then how we're going to handle this. So that's why this checklist, you may be going through your design and checking off different parts of this checklist. For today, we're going to be checking off the roof system and some of the connections, but we're not even going to touch the floor and wall systems. So those will be unchecked if you're working through your design. And if you're designing over a couple of day period and have to come back to it, that checklist may come in handy for you. So let me just double check here, make sure I haven't blown past any polls that we're supposed to take. I told Michelle and Marcy if I do that to interrupt me, but I think I'm on target here to jump into the roof story design. And so if you're following along in the workbook, we're on page 13, and we're going to look at the roof and ceiling framing. Then we're going to look at roof and ceiling sheathing. We're going to talk about wall framing and connections, and then there's a nice little summary at the end that we'll look at right before we jump into some of our Q&A. And I also told Michelle and Lori and some of the folks who were helping with the Q&A in the background, if you have some questions, if I gloss over something too quickly and you need a clarification, I've given them permission to interrupt me and make some clarifications along the way. So feel free to ask some questions along the way. If they're able to answer them for you, I think they're going to do that with the chat box. But if it's something that we see a lot of people asking about, they may interrupt me and ask me to clarify some of that information. So let's look at roof story design on page 14 of the workbook. And one of the first things you see up here in the upper right hand corner that should help you to follow along is just a little icon or graphic that we use to kind of help you know where you are in the structure. So this is a two-story structure with an attic space, and so this little gray bar or gray box here tells you that one of the first things we're going to be looking at is this finished attic space. So this is the finished attic in that roof. Over here on the left, the clear box is the vaulted ceiling, and we'll look at that next. But as these boxes get grayed in, that kind of gives you a sense in the workbook of where you are in the process. So we're going to look at the finished attic first, and I'm going to talk a little bit about the difference between rafter ties and collar ties, and so this gives you a good idea of the cross section of this finished attic. And we've got some collar ties up here in the top of the attic space, and the purpose of those collar ties is to hold this roof system together. So this handles the roof uplift that's on the structure, and that collar tie, and that could be replaced by ridge straps that strap across the top of the building, and there's some exceptions for that, but if you use a collar tie, that is to keep this ridge from opening up and resist those uplift loads, those suction loads on the roof system. So then in this particular case, we've got floor joists in our attic that span across the entire system. There's a load-bearing wall here in the middle, so we're going to have 16-foot joists, floor joists in that attic system across that 32-foot roof span. So for our rafters at 16 inches on center will span, I'm sorry, these are the rafters. I should clarify that. These are 16-foot rafters. This is the ridge across that 32-foot roof span. And this part of the finished attic is about 25.5 feet along the 40-foot length. And then we've got that stair opening right here That's only about 12 feet long, and so if you recall, we've got some limitations on diaphragm openings. We're within those limitations with this 12-foot limit. Our ceiling joists, which are also doubling as floor joists, are at 16 inches on center, and again, they span that 16 feet to that load-bearing wall. And so that's our ceiling joists and our rafter spans. Then, over on the other side of the building, on page 15, this is our vaulted ceiling. So you see the graphic up here at the top tells you we're in the vaulted ceiling, or raised ceiling, as we call it here. And so we've still got the collar ties up here, but in this case now our floor joist has become what's called a rafter tie. And a rafter tie is the nomenclature that we use to indicate that we're no longer just a ceiling joist or a floor joist, but now we've moved into the attic space itself. And that's going to create some additional moment here on these rafters that we're going to have to deal with in the design process. And so that changes the span of our rafter ties from what we were able to do earlier with that load-bearing wall in the middle. So now we've got 21-foot rafter ties. Now we don't have a roof, we don't have a floor load on that anymore. So we'll see how we size those in just a second. But our rafters are going to be still 16-foot spans based on the horizontal projection. But again, because we've got some additional moment here on those rafters because of this tie, you're going to see that changes the design for these roof rafters here. So I'm going to jump now to the next page, and I think Marcy's probably coming now with another poll question for us to make sure you're all still with us. So Marcy? Marcy, I heard you for a second and then you disappeared. I'm not hearing your audio. There
Sorry,
you are.
I must have double-clicked my little button. So,
all right.
all right. A collar tie is located in the blank of the attic space. So the upper third, the middle third, lower third, or none of the above. All right. And our folks are voting. 65%. So let's get 80% of you voting. About 5% more. Right, I'm going to close and share. The majority of you say the upper third. 93% say the upper third. All right.
And that is the correct answer. And so let me just review that real quickly again. Collar ties are defined as being in the upper third of the space. The rafter ties or ceiling joists are in that lower third, and what those rafter ties are doing is they're resisting this thrust of the walls, and that's kicking some extra moment into these rafters here. And so they serve two different purposes. The collar ties handle the uplift and keep that ridge from opening up. The rafter ties sort of bind these walls here at this lower level together and keep those walls from spreading out. So that's the distinction between those two, and you'll see how that plays out in the design. So we're going to jump to rafter design, and you might think this is a pretty easy process, but one of the things that we'll be looking at as we go through this example here, and we're going to start with the finished attic here, and again that gray bar shows you where we are. And we're going to look at a ceiling, which means gypsum attached to the rafters. So that's going to cause our L over D ratio for that finished ceiling to be L over 240. So that's one of the limits we'll be looking at. Remember, our ground snow load is 30 pounds per square foot. Our live load is 20. And our wind load is 160. So we're going to actually check all three of these loading conditions for the rafters to make sure that this works. And so to do that, we're going to, again, jump sort of to the back of the book. And so give me a second to navigate to table 326B. And so if you're following along in the wood frame construction manual, Let's get to table 326B, and let me expand that for you so you can see it. We've added some text here, bold, big and bold, to try and give you a sense of where you are in the table. So we're at live load equal to 20 and L over D of 240, so that makes sure you know where you are, and that's, as you recall, a ceiling attached to the rafters. And so let's size this. It's on page 281 of the wood frame construction manual. So we've got, as you recall, a required span of 16 feet. And I want to go ahead and jump right into the footnotes. So it'll help us to figure out what we're doing in the example problem here if we tackle those footnotes first. So we're in table 326B in the wood frame construction manual. Jump down to page 282 and you'll see the footnotes here. So for this particular one, we can ignore the footnote 1, because that's for a vaulted ceiling that we're going to tackle next. So we're going to skip over footnote 1. We'll come back to that. Footnote 2 is for our sloped roof adjustment factor that's permitted per ASCE 7 for roof pitches greater than 4 and 12. And so for this particular example, we've got a 7 and 12 roof pitch and a 10 PSF roof dead load. That factor is 1.05, and that's the factor that shows up here in our workbook example. Then example, or footnote 3 in our workbook for exposure B wind load conditions gives us the wind load adjustment factor on those rafters. So as we've mentioned, 160 miles per hour puts a pretty good wind load on the structure, whether it's direct load into the structure or suction load out of the structure. And so this adjustment factor allows you to modify your live load rafter span to account for that wind loading condition. Again, there's a lot of calculations behind this little table here. Don't have time to go into all the background for it, but for an exposure B, 160 mile per hour zone, and for the 7 and 12 roof pitch, again, there's all kinds of different roof pitches here that you have to look at, but for this particular example, 7 and 12 is the only option you've got, and that gives us an adjustment factor of 0.95. So the commentary, again, gives you background on this, gives you background on these adjustment factors here. So for time purposes, you're just going to have to trust that these answers that we're pulling out of here are right for this example, and you can look into the background for those on your own time. So I'm back here to table 326B, and we're just going to take the first one. Just notice that we've solved this for Doug fir larch, hem fir, southern pine, spruce pine fir. So no matter what part of the country you're in, you probably have one of these options here. And the yellow indicates that all of these options work. We've got green here. It shows that we've made it work. Notice these little trial and error icons out here means that this is a trial and error process. So we may have to go to the span tables and pick a span, a rafter span, but then once we adjust it, some of these adjustment factors are greater than 1, some of them are less than 1, and so you'll see that that may require a trial and error process. But let's look at a Doug fir larch, 16-inch on center, rafter span, number 2 grade, and so we're going to jump into this rafter span table here, 326B. So 16 inches on center is our spacing, and we're Doug fir larch up here, number 2, and we're moving across, and let's see, we need a 16-foot span, so a 2x6 won't quite work. That's only 14'4", so let's look for this one, which was 18'11", and whoops, that's sorry, 18'5". I was in the wrong row there. 18'5" for number 2 grade. And we see that matches up with what we've selected here in our table. So now for the live load application, we can take that 18.4 foot span and we can apply, if we had a thrust load, we could apply that, but we're just going to apply the sloped roof adjustment factor to that, and we see that'll span 19 foot 4. So that works greater than 16 feet. That the 2x6 wouldn't work because that was only a 14-foot span, and this adjustment wouldn't have gotten us to where we needed to be for that. So now we can check our wind load adjustment because we've already picked our wind load adjustment factor of 0.95, and that reduces the span because that is creating additional load above and beyond the live load on the structure. And so we take that same 18 foot 4 and we can apply both of those factors cumulatively to it, and we end up with an 18 foot 4 inch span. And so kind of note we jump back and forth between decimal 18.4 and inch foot and inches, which is 18 foot 4 inches here. And then we're going to check our snow loads. So for that we're going to have to jump to a different table, 326D. And so I'm going to come back over to my wood frame construction manual, jump to 326D, and that's here. And remember, that's a ground snow load of 30 pounds per square foot, LOD of 240. We're going to come down here to 16 inches on center, our Doug fir larch number 2, and work our way across. Oh, that 2x8 won't work anymore. So now we're going to have to jump to a 2x10, which is 18 foot 9 inches. So that's what shows up here in our table. And that's only able to be adjusted then by the thrust factor. For this particular case, for snow loads, you don't take the sloped roof adjustment factor. You don't take the wind load adjustment factor. So we've calculated our live load span, we've calculated our wind load span, and we've calculated our snow load span. And because this one requires a 2x10 instead of the 2x8, that's why this one controls the design. So it's a 2x10 required for the snow load, in this case 30 pound per square foot snow load, to get that to work. So hope that gives you an idea. Check the footnotes here where we talk about 2x12 might be needed for bad insulation. There may be other things that would be required for other reasons in your rafter system, but for this particular design 2x10 works. Then since the thrust is accounted for, we can use a ridge board in this particular example. I think the code requires that you be one size larger, or at least that same nominal size. Let's see. This actually may need to bump up to a 1x12. I think you need to be one nominal size larger than what's required. So that may be something we have to edit in the next version of this. However, here's something that may be of interest to you. If you wanted to design a ridge beam, there is a table in the wood frame construction manual that will allow you to design a ridge beam. And if you were to do that, then you've got all kinds of other load path requirements. You might have to use stud packs in the end walls all the way down to the foundation, and then that foundation would have to be oversized to handle that roof load all the way down through that wall. But this shows you that if you wanted to do that for that, let's see, 25'6" rafter or ridge beam over that finished attic, you could do that with a 5 1/8 by 19 1/4 1.5E glue lam member. So we just throw some options in there to show you what's available to you. I hear somebody. Yes, Michelle. Thank you.
Couple questions came in.
Yep.
One is, and I believe you covered this at the beginning of the webinar regarding the wind loads and that they're based on ASCE 710 wind speeds. Could you go over that real quickly again? Just a review.
Good call. Let me get back into the commentary for that, because there's a table here, and if you're in the IRC, this is really confusing, and this gets fixed in the 2015 code. But let me actually jump to the front end, because that's where this shows up. So here's the deal. if you are in the IRC tables are based on ASCE 705, and that trigger of 110 is for ASCE 705. So they've got this table, this conversion table in there that shows you that for the equivalent ASCE 710 basic wind speed, it's actually 140. So for our example here in the wood frame construction manual, when we converted this over from the ASCE 705, we were at 120. We went to ASCE 710, and so I rounded up to 160 instead of rounding down to 150. A lot of parts of the country have rounded down to 150. So this little table here is comparable to what's in the IRC. It's the wind speed conversion table. I know it's confusing, but everything in the wood frame construction manual is based on ASCE 710 wind speeds, and for our example, we're right here between these two. We're at 160, which is between the old 120 and 130, if that helps you at all. So these are all wind speeds based on ASCE 710.
Okay.
You think that takes care of it, Michelle?
I think so.
Okay.
One other question that came in, a few of them came in regarding the design of the roof system. They said in their area of the country, rarely are they seeing these types of roofs. They're seeing more about the truss system, wood roof truss systems, and where is that?
Yep. And so in the wood frame construction manual, there's a whole section in Chapter 3 that says if you have a roof system, that's to be a roof truss system, or a roof i-joist system, which is also used in some applications. Those are per the manufacturer. So those are designed typically by professional engineers for those systems, and that's the way the code is written to address i-joist and truss engineered wood product type applications. We show rafter systems here just to give us a chance to use those requirements. We know some stick framing is still done in certain parts of the country, so we understand that that's not necessarily the predominant use in the country, but those engineered systems are designed by a separate manufacturer, typically a professional engineer with that manufacturer.
And there's a portion of the wood frame construction manual, the 2.5.3, that covers the wood roof truss system. Okay, that's it.
All right, great, thank you. All right, so back to our example. And so now we're going to look at the raised ceiling, and I'm going to keep moving quickly because we'll run out of time if I don't. And so this is the vaulted ceiling over the bedroom, and this is also a finished ceiling. But in this case, the rafter tie is up a third of the ridge height from the top plate. Okay, so what's going to be different about this particular example? Everything is going to be the same, except this thrust span adjustment factor, footnote 1. So I'm gonna jump to that table, and that's going to be the snow load table, which we're in here, the ground snow load table. Actually, that applies to the other two tables as well. But that so let me go back up here. Sorry about that. So that we can all be on the same page. So I'm in the footnotes on page 282, footnotes to table 326A and B, and this gives that adjustment factor, that thrust adjustment factor, and for being a third of the distance from the plate to the ridge, that adjustment factor is 0.67, and that's a pretty significant penalty on your span. And again, it goes back to, and you can see it here in this workbook, in the wood frame construction manual graphic here, where that rafter gets raised up into this attic space. We're putting a lot more load right here, putting a lot more load in the rafter at this location because of the increased moment here. So not only are we resisting the snow loads or the wind loads on this rafter, but because we've moved this tie up into the rafter system, it puts increased moment here, and so that's what this penalty is on the span. And so that penalty shows up here back in the workbook on page 17, table W 4.2. It shows up here for the live load span, it shows up here for the wind load span, and it shows up here for the snow load span. And so all of those account for that increased moment. Again, this is a trial and error process, so what happens is we go into those tables, we actually have to check 26 foot roof spans because it's going to get reduced by this 2/3 adjustment back down to 18 feet. So we end up with 2x12s in that system at 16 inches on center for the live load span, 2x12 at 16 inches on center for the wind load span. And then, wow, we get to the ground snow load, we have to go to 2x12s at 12 inches on center to make that work for 16 feet. And it's all because of this penalty right here, that 2/3 penalty for that rafter tie that gets raised up into the system. So that's the difference there with that raised rafter tie. And again, we show the option here for ridge boards versus a ridge beam. So that 13-inch deep ridge board could be used, or depending on, well, let's see, what do we say here? Right, we didn't show the ridge beam option here, so this would just be a ridge board over that vaulted ceiling since the thrust is taken care of. So I've got a note here that Marcy's coming back to us with a poll, and so I'm going to turn it back over to Marcy and let her take this next poll for us.
All right. So roof rafters are designed to resist A, wind loads, B, snow loads, C, live loads, or D, all of the above. And this is going to be a quick poll, I think.
Yep, it looks like it. Good, good.
Excellent.
I hammered that point home, so that's very good. Everybody's on board.
All right, I'm going to go ahead and close it and share. Everybody is saying all of the above, and even Marcy, who's not technical at all, knows.
Excellent, excellent. Okay, well done. Yes, all of the above. You saw that in the example problem, and so we'll just keep on moving now to ceiling framing for our finished attic. I'm not going to spend a lot of time here because this is very, very similar to what you would do for a floor joist application. The tables are very, very straightforward. Let me just jump to those quick here in the wood frame construction manual, table 318. And Marcy, you may want to mute yourself. And 318. Oh boy, I should have jumped ahead and rolled back. But these are the floor joist spans, and for this particular sleeping area, 30 pound per square foot, and you pick your spans out. Not a lot of adjustment factors for that one, so this is really straightforward. We end up with 2x10s at 16 inches on center. Then the other table that's pretty handy is a floor sheathing table, table 3.14. And so this is for table 314, maximum floor sheathing spans for live load. So it's pretty much all inclusive there, and you can see that you need 19/32 inch wood structural panel single floor applications for that. So again, not going to spend a lot of time on that. You end up pulling that from this table here, and those are pretty easy lookup tables in lots of literature. Here's a good exercise for you. Back in the workbook again on page 19. Not going to take time here because we're pressed for time, but mention that raised ceiling joist in that for that vaulted ceiling. It doesn't have a floor load on it, but it does have a ceiling, so it's L over 240. The span is actually a 21-foot span, so that pretty much may exceed any ceiling joist tables that we would have available. So one of the ways that you can do that is either with a calculator, and we've got an online calculator on our website that you can go take a look at, or you could actually go with a NDS tabulated value, and from table 2.12a in the wood frame construction manual, it tells you the required E and bending values that you need for that particular ceiling joist for a 2x6 or a 2x8, and then you can size those ceiling joists based on NDS supplement capacities. So again, it's a trial and error process. It won't take a lot of time here. We won't be able to finish everything today, but that's another exercise and just another way that you can use the resources, especially for you engineers in the audience. That shows you some of the flexibility in Chapter 2 and some of the loads and load requirements that are calculated for you in Chapter 2. So take a look at that pretty much on your own time, and we'll just keep on plugging along through the workbook here. So we're on page 20 now. Roof and ceiling sheathing. We're still in the roof system, and so we're looking at ground snow loads, live loads, dead loads for our roof and ceiling sheathing. So we've already designed our rafters, but in tables 3, 12, A and B in the wood frame construction manual, let's get there real quick and make sure again you're in the correct exposure category. You can see that for the wind loads, 160 mile per hour, and for different rafter and truss spacings for wood structural panel sheathing grades at 16 inches on center. Over here under 160 you could use 3/8 inch wood structural panels, and that works for wind, and down here for the roof and snow load table 312B. That also works. I'll be honest, I would be kind of scared to get on a roof with 3/8 inch wood structural panels myself, but that's what it designs out for in the literature. So for those live snow and roof loads, that will actually work. Now the nailing for that is going to be pretty substantial. So when we start looking at suction loads a little bit later on, actually getting that nailed to the roof may require, and keeping it on the roof may require some additional nailing. But that's pretty much for the inward loads on the structure. Now let's talk about roof diaphragm bracing in the finished attic. So one of the things that we need to make sure of with our load path is that we, and this figure 3.7b is what's recreated here. Let me try and highlight it for you. This figure shows that for the rafter system, that we can either brace that roof diaphragm with blocking here at 4 foot on center, and then there's some fasteners nailing requirements for that blocking. So this is a prescriptive way to block that roof diaphragm after you get past a certain wind load. I think it's 130 mile per hour wind load. This blocking is or diaphragm bracing is required. So this is the prescriptive approach, pretty easy blocking in that rafter system in those first two bays. Or, and that's why we have or here, you could use the gable end wall with that attic floor and ceiling to brace that gable end wall as well. And so this is allows us to use table 315B of the wood frame construction manual. So if you want to go there, and you can see, again, choose the right exposure category B. We're on page 199 of the wood frame construction manual. And we're going to look at the wood structural panel provisions, because this is an attic floor that's got wood structural panels on it. So we don't, in this case, have gypsum. We'll look at that one in a second. And so we've got our wind speeds here. We've got our roof pitch here. We've got our roof span, which in our case we're going to interpolate between 24 and 36 feet. So we come over here and see that we're going to have to interpolate between 8 and 12 feet. And so we've done that interpolation for you over here. And that's 10.67 feet. And so we've got one more footnote to take a look at, which is this one, which is footnote 1. So let's just scroll down past exposure C to page 201, and it says that we are assuming sheathing continuous from gable end to gable end. So if we're only blocking one end, we need to multiply that by 0.84. So in this case, since we've got a partial diaphragm with that finished attic across the roof system, we've got that adjustment factor of 0.84 to apply here. And so that ends up being, let's see, 8.96 feet. And that's actually less than, there's another trigger here somewhere. I think it's in one of the footnotes or one of the provisions of the code that says it cannot be less than 1/3 of the distance. And so to maintain that 3-to-1 aspect ratio, yeah, here it is. Footnote 1 says, in no case shall the length be less than 1/3 the distance between bracing walls. So that's why that 10.67, it's actually coincidental there that that's what was calculated, I believe, from the table, but that's why the 8.96 is too small with that adjustment factor, so you actually have to go with 10.67 or 1/3. And we've got plenty. We've got about 25 feet of attic floor, so we don't have to worry about having enough. Now let's jump to the raised ceiling provision. So again, you could block it at the roof system. If we do that, though, we would then potentially have to balloon frame our studs on that end of the wall, and then we got to look at our wall system in a little bit with that balloon framing and make sure we can balloon 18 feet with wall studs. So if we do that, that means some balloon framing, some additional detailing, or we can go again back to table 315B, and in this case we're going to take a look at two different things. We'll look and see if the gypsum will work, and so I'm going to jump up here to the table again, get into the exposure B table. Let's look at the gypsum diaphragm and see if there's enough capacity there. At 7 and 12, I'll come across. That's hard to do with. We're here and interpolating between 21 and 35 feet. So that actually, something doesn't seem right here for that interpolation. Give me just a second to get my bearings. sorry about that. I may have misread that table at some point, or maybe I'll figure it out here in a second, but I'm thinking it's supposed to interpolate between 21 and 35 feet. We, for some reason, have 18 feet here, and with the adjustment factors, it ends up showing 16 feet of gypsum. So we know that gypsum in this particular case won't work. So we're going to end up having to sheathe that ceiling assembly with wood structural panels because of all the adjustments that we have to apply to this particular example. So I'll have to go back and look and see with that particular example why that number is not working out for me. But for the wood structural panels, when we come up here and look and interpolate like we did before, we're going to have plenty of capacity. Oh, I know what it is. It's the roof span. So I'm interpolating between 24 and 36 feet when the roof span in this case is actually 21 feet because of that raised ceiling. So that kind of throws the calculations off a little bit. So the roof span is 21 feet, and so that's why those numbers are smaller in this particular case. This is the roof span that you have to look at. So these are the numbers you end up with. That means that you have to sheathe that vaulted ceiling with wood structural panels if you're going to use that to block that end wall, that end wall on the structure. And then, in addition to that, see this figure here, 3.7a, you're going to have to make sure you've got sufficient blocking into that system to keep a hinge from forming there where you are framing up to that height. If you're not balloon framing, if you're only framing up to that vaulted ceiling and then using shorter studs above that, you're going to need to make sure you block or use this detailing for that ceiling diaphragm as well. So those are a couple things that you need to be aware of just to take care of some of the load path. So if you balloon frame, again, you can block into the rafter system. If we're going to use that ceiling to do the resistance here for the diaphragm, or use that ceiling diaphragm to resist these gable end walls, then some special detailing is going to be required. So we'll get to that in just a second as we move on through into the wall framing system. And I think we're still on track here to finish up on time and leave some time for questions. So let's move to the wall framing section. And so take a look at the drawing up here because this is showing kind of where we are. This is that gable end wall where we've got a vaulted ceiling. It's a non-load bearing wall. So we'll look at some of the non-load bearing wall stud tables here in a second, but there are basically two options that we've been talking about to design these end studs. We can either balloon frame them from the second floor all the way up to the rafters, and that means that's an 18-foot balloon frame. Or we could go up about 12 feet to that raised ceiling and then go another 6 feet above there up to the rafters. So for option 1, and I believe this is the balloon frame option, let's jump to tables 320B and let's do some design with the stud tables. So let me get there, and then let's jump to table 320B1, and I'll tell you in a second the difference between 320B1 and the 320A tables. So before I leave 320A6, I'll just point out to you that these tables are for studs that are fully sheathed with what we call minimum sheathing material. That could be foam sheathing or some sort of minimum sheathing material that does not give you the composite action that a wood structural panel will give you. So that's the distinction between the tables with the A designation and then where we're going, which is table 320B1, and that is fully sheathed with 3/8 inch wood structural panels. And so I'll take a little bit of a break here to talk to you about how those wood structural panels provide some additional composite action for the studs. And this is actually standardized in the wind and seismic standard, but if you're familiar with repetitive member factor, C sub R, in the NDS, that allows you to take a 15% increase on bending for studs. 15% increase for bending on any kind of bending member. And the studs in this case are in bending due to the lateral wind loads. In the wind and seismic standard, what we allow as high as a 1.5 repetitive member factor for 2x4 studs sheathed with 3/8 inch wood structural panels on one side and 1/2 inch gypsum on the other. And so these tables all have that 15% increase built in for those bending design values. The other thing I need to share with you, and this is something we get questions on all the time, is do these stud tables account for combined bending and axial loads? And the answer there is no, because we have an interpretation from ASCE 7 Wind Loads Committee that you do 2 checks on studs. One check is the check for combined bending and axial, but in that case, for the wind loads, the bending loads for that combined bending and axial are main wind force loads, which are much lower than component and cladding loads. The second check, which we're doing here in this table, is bending only using component and cladding loads. So it's 2 separate checks, and what we've found in our analysis and what's sort of in the background, or in the commentary to this document, is that combined bending and axial load check using main wind force loads does not control for the wood frame construction manual studs over what's shown here in these tables, which look at bending only using CNC loads. And so if you haven't heard about that, there's a document on our website that provides details on that. We can get you a link to that document so you can prove to yourself that that is indeed the case. But that is what's, and if you go to the commentary for this table, you'll see that that is the assumption built into these tables. So that's for some of you designers out there that want to know, what's behind the black box. Let's get back to the selection tables now, because we're going to run out of time if I don't do that. So I'm going to size these balloon frame tables, these balloon frame studs up to 18 feet. So let's see if I can do that. We've got 160 mile/hour wind loads. Again, make sure you're in exposure B tables. It has this H over 180, 3/8 inch wood structural panels. I'm on page 243 of the wood frame construction manual. You got to be real careful that you don't end up in the wrong table. 160 mile/hour wind loads. And just trust me, I couldn't get 16 inch on center framing to work for 18-foot studs, so we're going to look at 12 inch. And let's just do the Doug Fir Larch number 2 and work across here, and it ends up requiring a 2x6 to get that 18. It's actually 19-foot 5 that works, so for our wind loads that works, and for a non-load bearing stud, the maximum allowed by the code is 20-foot length for that, so we're still within the code limits as well. So wind loads work at 19.5, and the code allows for dead and live on those non-load bearing walls of 20 feet. So we could actually increase that spacing once you get to within 4'5" on either side of the ridge, where that height drops below 18, drops below what will work for 16 inches on center. So there's some things that you can do to get that spacing to work, but I don't know that you'd necessarily want to mix and match spacings in a gable end wall. But look at some of the footnotes on that. Option 2 that we talked about earlier is actually the one that we'll end up choosing later on in the design process, but that's just to frame up to that raised ceiling and then frame the rest of the way with shorter studs up here. That's covered in this table here, table W4.6, where we sized those studs, and in this case, number 3 stud grade material works for 2x6s. And the reason we chose this option is so we could keep the grades the same for the studs throughout the structure. But that hopefully gives you a sense of what happens with balloon framing and what's actually required on some of those for bending loads on some of those stud walls with these high wind applications. So I'm going to jump next to the connections, and as we begin to wrap up here with the connection provisions, again, I want to leave enough time for some Q&A at the end. So we're going to look first at our lateral framing and shear connections, and we're going to look at the roof to wall assemblies, and we're going to look at the rafter ceiling joist to top plate. So if these were trusses, you could use these similarly for trusses or i-joist to design this particular system. So again, we're 160 exposure B. Our rafter and joist spacing is 16 inches on center for most of the roof system, but if you'll recall, and this is another correction or addition I have to make to this this document, it went to 12 inches on center for that vaulted ceiling. So I'll have to show you a couple other footnotes to apply to this example problem, but we're going to look at the attic space for this particular portion here. And so for these walls 2-1 and 2-2, the wall height's 9 feet and the top plate to ridge height is 9.3, and so I'm going to jump now to table 3.4 in the, oops, sorry, let's get rid of that. Bear with me while I get to table 3.4. I believe it's A, because this is the prescriptive table, and in just a second I'll show you another option. So table 3.4A is the prescriptive rafter ceiling joist to top plate lateral and shear connection requirement. So again, make sure you're in exposure B. This table, and if you look at the commentary, looks at both lateral and shear connections. So we've designed for wind loads in both of those directions to see what controls, and that's what we tabulate here. So 160, 16 inches on center. We got to interpolate between 8-foot and 10-foot roof heights, but that's real easy in this case because they're both require 3 8-penny common nails or 10-penny box nails toe-nailed at the end of those rafters. So that's what you have there. I'll direct you to footnote 4 real quick just so you see that top plate to ridge height could affect these numbers here, but we're at 9 feet, and so it kicks in above 10 feet. So that adjustment factor is 1. So now let's see what's next. Top and bottom plate to stud lateral connections. These are on the gable end walls. So we designed the load-bearing walls. Now let's design the connection at the non-load-bearing walls, and for that we'll go to table 3.5A in the wood frame construction manual. And so 3.5, again I'll tell you in a second the difference between 3.5 and 3.5A, but exposure B, we're on page 178, 160, 16 inches on center. Our wall height is 9, so we come across here and we see that that only requires 2 nails, and those are required number of 16 penny commons or 40 penny box at the stud to plate connection. So those are in nailed through the plates into the studs, and so that helps with that load path. Now we're going to look at our uplift connections on page 25, and this is where we have our roof to wall uplift strap connections. For this one, I'm going to jump to table A 3.4, and so the reason these are in one of the supplements to the wood frame construction manuals. Most all of these strap type connections are proprietary, so we wanted to keep them in the document, but since they are proprietary connections, they kind of got moved into the appendix, but they're still here. So again, make sure you're in exposure B, 160 miles per hour, and then for 16 inches on center, and our roof span in this case is 32 feet, so we don't actually have to interpolate this one. It requires 4 nails. Always look at the footnotes down here. In this particular case, we don't have a wall dead load to offset anything, or a ceiling assembly dead load to offset that, and so that is your uplift strap requirements, the nails at the end of your uplift straps. All right, so now here's how I can tell you the difference between those prescriptive tables that I've been telling you about and some of the others. So this table, W4.9 in the workbook on page 26, shows the loads basically. So if you had a catalog of proprietary connectors and you just wanted to know what are the loads that I need to resist for my uplift connections, my lateral and shear connections, that's what these next tables are going to show you. So I'm going to jump back to table 3.4 of the wood frame construction manual. And again, exposure B, make sure you're in exposure B. I'm on page 167. Wind load 160, rafter truss spacing 16 inches on center, and we're going to move across here to our 32-foot roof span, and we see that that's 479 pounds of uplift, and so that's the required uplift connection. Again, looking at the footnotes, those in this particular case don't apply, so that's really what you would plow through here to see what footnotes apply. None of them do, so 479 is your final answer. And then we'll jump to the next column, which shows us the lateral connection for this one. And so it's 16 inches on center over here under lateral. We're at 224. Again, none of the footnotes apply for this particular example. And then the final one is shear connections. And so in this particular case, we're parallel to the ridge. And so this is this has a little bit more of a calculation you have to do. So depending on which way the wind you're looking at for this particular, it's 116 R. R down here is the length to width ratio. So in this particular case, our length to width ratio, or width to length, in this case is 0.8. So that adjusts that 116 times 0.8, adjusts that to 93 pounds. And then there is a shear connection adjustment here in footnote 4 that kicks in above 6 and 12, and at that top top plate to ridge height of 9 feet, which we have, and so that ends up being a 0.92 factor. So again, looking at all these factors, you can come up with your required shear connection. But it's a lot easier just to pull them out of the table where that work's already been done. If you want to run through the calcs, it's here. Again, to save time, I'm going to skip over the gable end walls, but there are similar tables for your gable end walls. Table 3.5 allows you to get your lateral capacity, and then you just look at the other direction for your shear capacity. Your length to width adjustment in that case is 1.25. So that gets us through those connections for the rafters to the wall system. Our roof sheathing system is in table 310 of the wood frame construction manual. So let me get there. And these are pretty straightforward tables, just showing what your nailing requirements are going to be. In this particular case, it's 6 inches at the edges, 6 inches in the field. And these are 8-penny common nails, by the way. And for the interior zones, you could go 6 and 12. And then for those gable end walls and rake overhangs, you have to ramp those down to about 4 inches on center. And if you've seen the figures in the wood frame construction manual that show where those high wind loads are, they're always out there at the edges. And that's why you're going to see so much of that. And you know what? I just realized that I missed a poll. So Marcy, I'm going to ask you to come back real quick, and let's take a look at our last poll before we finish out here.
All right. Let me launch that. All right, wind load connections between a roof rafter and wall top plate must be designed to resist uplift loads, lateral loads, shear loads, or all of the above. And once again, this should be a fast poll. I'm only going to give about 30 seconds for this one, so about 5 more seconds. And close. So 92% say all of the above. And
Excellent.
Just a few others.
Excellent. So yes, all of the above, uplift, lateral, and shear, are what we're designing our connections for. And this table here kind of looks at all 3 of those and determining uplift, lateral, and shear loads for our connectors. For the roof sheathing, again, I mentioned those tables are pretty straightforward. Then for ridge straps, if you decide that you don't want to use the collar ties inside of the rafters to keep the ridge from separating, you could go with these ridge tension straps that are in the back of the document. And so we were there a little bit ago. I'm not going to jump there right now, but in table 3A 3.6 there are ridge strap connectors, and if you were to look through those tables, you see that that requires 3 8-penny common nails in each end of those ridge straps. So if you want to get rid of the collar ties and use ridge straps on the outside of the rafter system or sheathing system to keep the ridge from opening up, you could certainly do that as well. You could also, from table 3.6, calculate those ridge connection requirements. Let me go one more to get to exposure B. And so exposure B in table 3.6, those wind loads, if you look down here, 7 and 12 and a 32-foot roof span, 351 pounds to resist there at the ridge. So getting close to the end here, these lap joints. So we want to figure out how to tie the parallel rafter and ceiling joist connections for the snow loads. So we've got those snow loads of 30 pounds per square foot, and we've got a roof span of 32 feet, so we're going to have to interpolate in this table a little bit. But we're in table 3.9a, and the 7 and 12 roof pitch, 16 inches on center. We're going to come across here, and it's either going to require 4 or 5, so we'll just round up to 5, and that's the number of nails required between the ceiling joist, or in this case it's a floor joist, and the rafter to take care of the thrust there at that location in those rafters. Alternatively, in table 3.9, which is just above, we could go in and actually calculate the load here for 7 and 12, and we come across to that 30 pound per square foot ground snow load. We'd interpolate between 454 and 681 and come up with 605 pounds. So you see how flexible these tables are. They allow you to size different components. The thing that you need to be aware of here is if we have a raised ceiling, now in the bottom of table 3.9 and the bottom of table 3.9a, we have to account for that additional thrust here for those raised rafters. So that vaulted ceiling, it's 1/3 of the way up. It's actually the inverse of what we calculated earlier. It's 1.5 factor. So for the number of nails calculated is 4, we'd bump that up by 1.5, and that would require 6 nails in this case. If we calculate the interpolated load at 454, that bumps up to 681, again based on that raised heel, raised rafter tie. Then table 3.1, and I didn't get to go there earlier, so I'm going to do that right now, just so I can show you the catch-all table. If you don't see a table that provides some answers for your load path, go to table 3.1, because that's the nailing schedule for just about every part of the structure. And so for our roof framing, it sort of maps out for you your rafter to top plate, ceiling joist to top plate, ceiling joist to parallel rafters, and tells you where to go in the document to get that. And if there's no table for it, then it's going to be provided prescriptively, like the blocking to rafters here that we're showing in this solution here on page 29 of the workbook. So this actually comes from table 3.1, and then if you've got a rim board to rafter connection on the gable end wall, that's another solution. So Michelle and Lori, I'll give you a heads up as soon as I finish this summary table. We're going to be ready for some questions, but take a look at page 30 because that provides a nice little summary of everything that we've worked through as far as the stud length, stud spacing, roof to wall connections and loads, and then for our roof and ceiling framing and connections, we've got what's required for the attic space, and probably be pretty silly to do a 2x10 in one span and a 2x12 in the other. So rafters will probably not be necessarily used. You probably use a truss system. But again, this is an example problem, and so it gives us a way to show you some of those differences, especially how you see a difference between just a normal attic space requiring a number 2 2x10 and a vaulted ceiling requiring a number 2 2x12 at 12 inches on center. And then some of the other requirements as well. So that's a good summary table to show you some of those differences. And I'm going to stop there and ask Michelle to join me and see what other questions we might answer here for part 1.
Okay, buddy. We've got a very active audience. This is great on all the questions.
A lot of information to digest at one time. So
right. One question came in regarding diaphragms, I believe it was referring to, or he or she was referring to, related to use of nails as opposed to staples. is there options to use staples in the wood frame construction manual?
So the capacities for stapled diaphragms are either coming from a group like ISANTA, the International Staple and Nail Tool Association. I'm not sure if APA has any capacities for stapled diaphragms or not, but if you can determine the capacity of your stapled diaphragm, and then take a look at the commentary to the wood frame construction manual to see how that matches up with the assumptions that we make for the diaphragms in our tables. I think it's around table 316 as I recall. So these are the roof diaphragms and then the floor diaphragms that we started out with in the discussion. Go to the commentary, see what the assumptions are for your stapled diaphragms. If they match up or exceed what we've calculated here, then you may be able to do something like that. But that requires engineering judgment and approval by the code official.
All right. Okay, there are multiple questions about the whole system related to collar ties, rafter ties, when does a larger ridge beam required, and just how that it all works. I think would be, if you could do a quick overview of how the loads are transferred. Because I think some may be confused. You're dealing with uplift loads and all that.
Yep. Yeah. So we'll go back to page 14 of the workbook as a place to start. And so I mentioned the collar ties, which resist the uplift force, keeps the ridge from opening up. And then in this case, we've got a ceiling joist, which ties the tails of the rafters together. If we've got a raised ceiling, then this rafter tie moves up into the attic space, and so now we've created more moment right here on the rafter. And so that's why those factors kick in, not only to upsize the rafters, but to upsize the connections to those rafters. I think I forgot to mention that here in the middle, where you're going to splice your rafter ties together, well, no, not this one, but above, up here, where you're splicing your rafter ties or ceiling joists together. You'll need the same nailing here as you've got at each end of the joist to make sure that you're carrying load through those as well. So that's all part of resisting those thrust loads out into the structure. So the other thing then that's happening in the other direction is if we have this raised ceiling right here, let's say that goes on up into the ceiling, and in that case we may have both a collar tie and a rafter tie. We may be framing the wall, the gable end walls, up to that point, and let me get down there to that wall framing detail. So now looking at it from the other direction, the gable end wall, we're now framing the studs up to that location and probably putting a wall system here to correspond to that raised ceiling. And so that's creating a hinge here, which means we have to detail to account for those loads in that direction of the gable end wall as well. And that roof or ceiling system that's here can also be used to brace the diaphragm, and that's what we calculated up above here for that end wall.
And then from a gravity, no wind load,
okay,
reducing the ridge beam too. I think there was some confusion on how the loads are
okay, right. Okay, so let me get back up here to talk about ridge beams versus ridge boards. And so on page 16, where we show an example of, so if you have the rafter ties or ceiling joists that are tying the bottom of these walls together to resist this thrust, then you could just use a ridge board. So you've already accounted for the thrust here taken through the ceiling joist or rafter tie. What the ridge beam allows you to do is eliminate that ceiling joist or rafter tie. So it allows you to eliminate this bottom member right here. But that's all that a ridge beam would allow you to do. You still have to tie the rafters together up here at the top, even if you've got a ridge beam. So you'd have to come across the top with ridge straps, or you could come underneath the ridge beam if you want to hide it with this collar tie, and the collar tie then ties those rafters together. Now, I don't know that they make hangers, fasteners that would allow you to connect the rafters to the glue lam beam. Let's say if you're using a ridge beam that would resist that uplift force. It seems like that'd be putting the nails in withdrawal in those hangers if that's what you're using, and so that's probably not a good solution, but you have to check with the hanger manufacturers about that.
Right. And then your compression of your portion of your ridge is not going to be braced if it's deeper than the rafters, I think, for reverse
Right.
movement.
Yes, right.
Depending on how deep it is.
Yep, that's a good point.
And the big difference, too, is that you're dealing with a system with the ties that span from wall to wall,
Yes.
as opposed to rafters spanning from the wall to the ridge, which then take the load out to the...
Correct. That's correct. So a ridge beam allows you to get rid of that thrust load that's pushing the walls out.
Yeah.
Yep.
Okay, the other question that came in had to do with your the commentary on cladding versus main force resisting system.
Okay. Yep.
And there is a white paper on our website, but I can't.
Let me try and get folks to that real quick. So if you're still following along on our website, go to the web page and then go to Codes and Standards. And let's see, what's the quickest way to get there? I want to get to Publications, and then we're going to go to Free Publications. So there's a couple different ways to get here, but if you can get to Free Publications, maybe you do a search on that. Once you get to this Free Publications page, over here on the right-hand side, scroll down on the right till you get to a little topic called Wind. All right, and then this paper right here, the second one in the list, is called Consideration in Wind Design of Wood Structures, from October of 2003. So it's over 10 years old. That's when we got that interpretation many years ago from the Wind Load Subcommittee, and that talks about the difference between designing studs for bending only using components and cladding load, or combined bending and axial using main wind force wind loads for the bending portion. And that's pretty clearly spelled out there in that paper. Shows an example, and that's something that once folks realize that we can do that, really saves a lot of time, one, but allows you to use stud sizes that we traditionally use for design.
Yep. Okay, it looks like we're coming up on the hour, so I think we need to let Marcy close us out, unless you have
Great.
something else.
No, thank you all for being with us today, and hope you stay or come back again next month for part 2, where we'll be doing some shear wall design and some floor diaphragm design and some other things that will finish up this structure. So thank you all very much.